All right. So chemistry 3111, where we left off last class is we finished like Kiliani Fisher and vol degradation and all that stuff. So we covered that. And I just started the section on disaccharides, I think, or I mentioned it or something. But as far as disaccharides go, there's I'll show you the ones that you need to know, and then we'll go back and talk about them. Okay, so the disaccharides that you need to be aware of as a 3111 student would be maltose. Okay, so you have to know what maltose is. You also have to know what cellobiose is. So cellobiose and maltose, you can see there's very few differences between them. It's just their glycosidic linkage that's different. And lactose, you also have to know lactose, which is another disaccharide. So far we've got maltose, cellobiose, and lactose. And I guess the last one would be sucrose. So sucrose, I think that's the last one. So that makes a total of 4. Okay, so there's 4 disaccharides you need to know. Okay, so again, I repeat, you have to know maltose and what that is. You have to know cellobiose and what that is. You have to know lactose, what that is. And the last one is sucrose, which is table sugar. Well, of course, you can't come out of organic chemistry and not know what table sugar is. So let's back up and go through all these. And sometimes I teach organic chemistry for nursing students. And this is one of the things that we always cover in that class is disaccharides. So somebody who's going into the healthcare industry should have a bit of an idea about some disaccharides. So we talked about monosaccharides. We talked about aldoses and ketoses, what that is. And so a disaccharide is nothing more when you take 2 monosaccharides and put them together or connect them in some way. Namely, we connect them via a glycosidic linkage, then we end up with a disaccharide. Okay, so disaccharides have a glycosidic linkage. Now, everybody knows what glucose is by now because we've talked about glucose this and glucose that. And one of the main take-home messages I think from last class was if you have glucose, so if you try to draw the chair of any of the monosaccharides, right? I said they always had this in common. So if we just zoom in here, I said this part that I have drawn right now, this part doesn't change for any glycoside. Now, what makes glucose unique is if we number our carbons, carbon 1, 2, 3, 4, and 5, and 6, like that. Carbons 2, 3, and 4, in glucose, all of the substituents are equatorial. So this hydroxyl group is equatorial, this hydroxyl group, and when I say substituents, I mean the hydroxyls, not the hydrogens. All of the hydroxyl groups are equatorial in glucose. Now, carbon number 1, we call that the anomeric carbon, okay? If the hydroxyl group is pointing down, it's alpha, and if the hydroxyl group is pointing up, it's beta, like that, okay? So alpha or beta. Now, that is why glucose is the most abundant of all the monosaccharides. It's because all of the hydroxyl groups are in an equatorial position at carbons 2, 3, and 4. And when we look at maltose, we see that maltose is actually 2 glucose molecules put together by a glycosidic linkage. Okay, now what do we mean by a glycoside? Well, if you remember from last class when we talked about glycosides, we said that that was an acetal. Okay, so an acetal. And if you search this entire molecule for an acetal, I'll show you where you'll find it. Where you'll find it is right here. It goes carbon, oxygen, carbon, oxygen, carbon. This is the glycosidic linkage between the 2 sugars. So you can see the two carbon atoms, 1 on the sugar on the left and 4 on the sugar on the right, and then they're connected by this oxygen. And you notice that the bond here, namely this bond, is going down. And so that is what tells us that this is a molecule of maltose. Why? Because we say it's got a glycosidic linkage, right? Because here's our glycoside, carbon, oxygen, carbon, carbon, oxygen, carbon, okay? It's got a glycosidic linkage. So again, I highlighted the glycoside, but we say it's alpha 1,4, or you see it says 1,4 and then alpha glycoside. So what is actually going on here? So this should actually be a letter alpha. So this is alpha 1,4 alpha glycoside. So there's 2 alphas here. The first one refers to in maltose, the bond going down from the sugar on the left, that is an alpha position, right? Because it's pointing down. So that is what gives you the identity of maltose, is you've got 2 glucose molecules linked together in a 1,4 fashion, and it's alpha 1,4, okay? Now, when it says alpha glycoside here, I mean, that could also refer a 1,4 alpha glycoside. You know what? Let's just, yeah. So maltose has an alpha 1,4 linkage, but I would also point out that at the hemiacetal here, that this hydroxyl is pointing down, so it is also alpha. Okay, so if the hydroxyl here was pointing up, you'd call it beta maltose, but since it's pointing down, you could call it alpha maltose. So again, what governs the identity of a person? It's their DNA. What governs the identity of maltose is that it's two glucose molecules bound together by an alpha 1,4 linkage. And if you peruse the internet, you'll see it sometimes written alpha 1,4 like that. You'll see it written a variety of ways. Okay, so yeah, so anyhow, now maltose is a reducing sugar. Why? Because if we have a reducing sugar, all it means is that we have a hemiacetal, so hemiacetal in the molecule, and you can see that we have a hemiacetal right here in maltose, and therefore it is a reducing sugar. So now if we turn our attention to cellobiose, cellobiose and maltose are very similar. What's the difference between the two? Because they're both made from two molecules of glucose. The only difference between the two is the way that the glycoside linkage is, okay? So in maltose, our linkage was an alpha glycosidic linkage between carbons 1 and 4. So this bond is pointing down, so it is alpha. Whereas in cellobiose, we still have our glycosidic linkage. Okay, there's our glycoside, right? But now the bond between carbon 1 and the oxygen here on the sugar on the left is pointing up, and so it is beta. So this one is beta, and of course it's labeled here too. But anyhow, so that, and if you're like, is that the only difference between the two? Everything else is the same? Yes. Now you see that they altered. They say this one here is the alpha anomer, and they put the beta here, but they could have just as easily put the beta here and the alpha down. It doesn't matter, okay? What governs the identity of the disaccharide, again, is the linkage, okay? Now we can see that cellobiose is also a reducing sugar. Why? Because it has a hemiacetal in it. So what's the conclusion? Cellobiose and maltose are both reducing sugars. Reducing sugars. It says they differ only at the stereochemistry at the anomeric carbons, and it should be pointed out here that it's the anomeric carbon where the glycosidic linkage is. So glycosidic linkage, like that. All right, so now that we have those two, maltose and cellobiose, we're going to see in a few minutes that maltose actually comes from amylose and amylopectin, whereas cellobiose comes from cellulose. So if you add more sugars to cellobiose, you get cellulose, which makes up things like, is found in things like wood and cotton, whereas maltose comes from amylose and amylopectin, which are forms of starch. Anyhow, now I'm sure you all heard of lactose, because we all know people who are lactose intolerant. I think that once you get to 80 years old, I think 80 years of age, I think something like 80% of the population is lactose intolerant by the time you get there. So make sure you enjoy your ice cream while you're young. But anyhow, you see that lactose is a disaccharide where we have galactose on the left, okay, and we have glucose on the right, and you see the linkage is beta 1,4. So it says a 1,4 beta glycoside is the way they're describing it. So 1,4, and this is beta because it's pointing up. So there we go. So now we have lactose, which is made from two different sugars. So we have maltose, which is glucose and glucose, alpha 1,4 linkage, or 1,4 alpha glycoside. Then we have cellobiose, which is a beta 1,4 glycoside, or a 1,4 beta glycoside. And then you have lactose, which is galactose and glucose, and it's also a beta or a 1,4 beta glycoside. Either way of describing it is fine. And you'll also notice, I forget to say this, that lactose is also a reducing sugar, because you see it's got a hemiacetal here. So we'll put reducing sugar like that. But then if we look at sucrose, sucrose is the only sugar that you need to be aware of that's not a reducing sugar. So it turns out that sucrose, which is table sugar, right? If you like to bake or something, or make cookies or put sugar in your coffee, you put table sugar in, okay? And it is a disaccharide that's made from glucose and fructose. You'll never be asked to draw glucose, sorry, sucrose or anything. But you can search and search in this molecule and try to find a hemiacetal. You won't find one because there's none in here, okay? So sucrose is not a reducing sugar. It says here that honeybees can take sucrose and convert it into sucrose, fructose, and glucose. And this is why I think that honey is actually, by definition, it's sweeter than sugar because fructose is sweeter than sucrose. I don't remember that exactly, but it's something along those lines. But there you go. So those are the four disaccharides that you need to be aware of. So let's review. You need to know maltose, cellobiose, and lactose. They are all reducing sugars. Maltose and cellobiose are both made from glucose. Maltose is an alpha glycoside. It has an alpha glycosidic linkage. Cellobiose has a beta glycosidic linkage. If you look at lactose, made from galactose and glucose, it has a big beta glycosidic linkage. And then finally, sucrose. Again, I'm not going to ask you to draw the structure or anything like that. You can see the linkage down here. Okay, this one here. Here's my pen. This one here is alpha because you can see it's pointing down off the sugar. But the main thing you have to remember about sucrose is that it's not a reducing sugar. All right. So let's see if we can determine whether each of the following disaccharides is a reducing sugar. It's not a loaded question or anything. It's just asking you, is there a hemiacetal in here or not? Because if it's a reducing sugar, it will possess a hemiacetal. All right. So let's take a look at A. So that's the first one here. Would A be a reducing sugar? Can anybody answer that? And there's no trick in here or anything. Is there a hemiacetal in this first one? Could anybody find a hemiacetal in there? Or no? So I'd say that this one would be a reducing sugar because it does have a hemiacetal, right? It goes carbon, oxygen, hydrogen right here. So this is a hemiacetal. So therefore, I would say yes, this is a reducing sugar. If we look at the next compound, you can see that you have a glycosidic linkage here, right? This is glycosidic because that's an acetal. And then we also have a glycoside here because this is an acetal. And so there's no hemiacetal in here, so this would be a no. This is not a reducing sugar. And the last one is kind of fast because it's sucrose. And we know that sucrose is by definition not a reducing sugar. So all you have to do is look for a hemiacetal. If you have one, it's a reducing sugar. If you don't, it's a non-reducing sugar. End of story. Now, in terms of disaccharides, let's review which ones you need to know. So the ones you need to know are going to be cellulose, which is a polysaccharide of glucose. And just like cellobiose, it's made up of beta glycosidic linkages. So you can see this is beta, this is beta, this is beta, right? It's beta 1,4 linkages. And cellulose, it says here, it can have strands of sugars that are up to 7,000 to 12,000 glucose units long connected through these beta 1,4 glycosidic bonds. And when it forms these long strands that can hydrogen bond, it's what gives like wood and plants their rigid structure. It's why the stem of a flower can be really long and then it can hold the heavy flower up on the top, is because all of the hydrogen bonding that can occur in these long linear cellulose fibers. Now, if you look at starch, on the other hand, which I'm sure you're all familiar with, okay, you know what, you've all heard of starch before. Well, starch is comprised of glucose units, and they're connected by glycosidic linkages. But you can see that the linkages here are alpha 1,4, right? So this is alpha, this is carbon 1 and carbon 4 here. So alpha 1,4 linkages, or 1,4 alpha, whatever. But when you look at starch, it's actually composed of two things, okay? It's composed of amylose, and this is the structure of amylose here. You can see it's just a straight chain of glucose molecules that are alpha 1,4 linked. But then it also is made up of amylopectin, which it's mostly amylopectin. And amylopectin has branches off of carbon 6. So I'll show you what I mean here. So it says here, amylopectin has glycosidic branches off of carbon 6. So that's amylose and amylopectin. And the book, I think, talks about water solubility a little bit, how amylose is not water soluble, but amylopectin is water soluble. All right, so that's all we need to know about monosaccharides and disaccharides. The part about amino sugars, I'll leave that as an FYI if you want to go over that on your own time. You're not tested on that. The same thing with the N-glycosides. I'll leave that as an FYI as well. You can see you're skipped. There's no questions about it on the final. So what did we cover? We covered the formation of a hemiacetal. And remember, when you have a hemiacetal, as is shown here, this tells us we have a reducing sugar. All right, if you have a hemiacetal. So you need to know how to go from the Fisher projection to a Haworth projection and then to a chair. You do not have to be able to do the same thing for a Furanose ring. So for a 5-membered ring, you don't have to be able to do it, so don't stress about it. Then we looked at all these different reactions. We looked at acetylation with acetic anhydride and pyridine. Then we looked at alkylation, which is like a variation on the Williamson ether synthesis. You use iodomethane, but your base is silver oxide. Then we talked about glycoside formation with methanol and HCl, and we talked about how you get racemization, or you get a mixture of alpha and beta at the anomeric center. Then we talked about the formation of an alditol. So this is an alditol. Then we talked about the formation of an aldonic acid. So this one here is an aldonic acid. And the reduction uses sodium borohydride, which we're familiar with. Whereas the oxidation to make an aldonic acid uses bromine and water at a pH of 6. And again, there's no mechanism provided for that in the textbook, so don't worry, you won't be expected to draw one. And then finally, to make an alderic acid, so alderic acid, we use the big guns, right? We pull out our nitric acid and water and we heat that up. Anyhow, so there you go. So that's a little bit about the reactions of monosaccharides. Then we talked about the Killiani-Fischer synthesis for chain lengthening. So this is Killiani-Fischer at the top, and then we talked about the vol degradation, which is where you break the sugar down, remove one carbon. We talked about diastereomers like glucose and mannose that only differ at one chiral carbon, and so we say they are epimers of each other, and that covers all of the material in the chapter. All right, sorry if you guys